Alrighty, we're going to talk about our final section in this unit, so section 7.9, where you're talking about exponential growth and decay and the application model. Okay, so our first example in your packet says let y be a function of time, and the rate of change dy dx is going to equal to ky, so k is some constant. And if we know that dy dt is directly proportional to y, then the proportion can be written as such. And so these are kind of common concepts that happen with exponential growth and decay. So first things first, let's talk about directly proportional versus indirectly proportional. Just a brief reminder of what that means. You know, directly proportional means my x and y are usually multiplied, whereas indirectly proportional will tell you you usually have 1 over something, or you have some sort of fraction involved. Okay, so how are we going to do this? We're going to take this step by step for example 1. So where do we start? We start with what we were given, which was that dy dx is equal to ky. We know what to do at this point because we did differential equations last time. Well, we're going to separate our variables, pull my y over, pull my dx over, and then we're going to integrate it, right? Because we're looking at our dy and we need to know what y is. We need to know our actual function. So we're going to determine our antiderivative, take that integral of both sides, and that becomes the integral of 1 over y is simply ln, and the integral of k dx is just going to add my x to my constant value. So there we get that. And then of course you're going to want to set it equal for just my y, which, you know, write our solution in terms of just y. And so to do that, we solve for our y, which means that we, to get rid of a natural log, we take natural base. So e to the ln, those cancel out, but on this side it won't. This is an exponential rule where if I have something to some power, if that some power is added, then it's actually the same thing as saying that those somethings, the bases, were multiplied at some point. And then what we know is that E of C is a constant, whatever that C value is, whatever my constant value is, because it's a natural base, whatever value I plug in is still going to be a constant. So I can actually pull that constant out and call this whole E of C my constant. We can relabel it big C, or we can label it big A, or any other variable we want to do, and it just becomes a constant, so it comes to the front of it. So that means y is equal to some constant value times e to the power kx, where k is our exponential growth or decay constant that we're going to be talking about today. And specifically what we're talking about, this is at that front of your packet, that if you have some y prime is equal to ky, where you know your constant k, then your k is your proportionality constant. This is what we just solved for. Similarly, of course, this could change because we could be using different properties, but k would be our proportionality constant. So when k is greater than 0, you have growth. When k is less than 0, you have decay. Okay, so let's actually use some true problems to discuss this. So if we know that the rate of change of y, so what do we know if rate of change means? Rate of change means I'm going to have my dy, right? Rate of change is our derivative, where that comes from. So our rate of change of y with respect to x. So this is saying our rate of change of y with respect to x. I'm just taking what's written, what's in my word problem, and transferring it over to notation. Is proportional to is inversely proportional to the square root of x. So it cannot be equal to my y. That would be directly proportional. It's inversely proportional to the square root of y. Okay, but we're not 100% done there because we're talking about our exponential growth. So what do we need right here? Well, we need that constant k. So k can just come over. And so what we end up seeing is to write this equation out, it's going to say dy dx is equal to k over the square root of y. To solve that, we simply do exactly what we did before. You separate your variables. So this becomes the square root of y dy is equal to k dx. We integrate. This becomes y to the 3/2 over 3/2, so 2/3 is equal to kx plus c. I could solve for y, get my 2/3 away, so this becomes y to the 3/2 is equal to 3/2 times the value kx plus c. If I distributed this 3/2, then 3/2 times my c, it's still just going to be some constant value. So this can actually be equal to 3/2 kx, plus still that constant value c. Just because that 3/2 is there, it's not going to change that constant value c is some constant value. And then to get rid of this, this is actually saying that y, the square root of y cubed is equal to this. So if I square this value, if I square this value, that's going to get rid of this square root. And then if I cube root it, it's going to get rid of this cubed. So that becomes y is equal to the cubed root of some 3/2 kx plus c squared. Okay? Moving forward, let's actually work on some true example problems. These are example problems that you would see kind of either these are similar to AP problems or they are direct AP problems, and they're all involving our exponential growth and decay. The concept here is very simple. You understand what your rate looks like, the original rate. You separate your variables, you integrate, and then from there you just have to understand what the question is asking you. If it's using words like at, then that means all you're doing is typically plugging in that t value. If there's some amount that was given before, like let's say you know that the price of a textbook started at $200 and then it's the change in price over the next 20 years inflated at this rate. Well, that $200 is going to be your initial value. So we'll see a problem like that. So you have to do initial value plus whatever at for rate change was. The only other one you're looking for is when it's not an at value, then it's going to be some sort of during or within or from to where, and that usually means that you're evaluating it. So instead of just plugging in t equals 4, you're usually evaluating it from whatever value till 4 or whatever till from A to B basically. Okay, so here we're looking for the number of bacteria in a cultural growth is growing at a rate. So we know we have a rate. So we're going to start there. dB over dt. Why did I pick these variables? Well, B, bacteria, that's just what's going on up here. And then with respect to time, because typically in word problems, we're taking with respect to time instead of x, but how do I know that for sure? Well, it says it right here, per units of time, so that helped me. And we know that it's going to be equal to this formula right here, 1500 e to the 3t over 4. Yeah, okay. And so what we can do is we can separate that variable. That one's pretty easy. Usually in these kinds of setups, it's really easy. All we have to do is drag my dt over, and then I integrate. Well, the integral here is just going to be my bacteria is going to be equal to my 1500 comes out times the integral of e 3t over 4 dt. Well, that one means I have to use a tiny bit of u substitution. That one's easy. U is equal to 3t over 4. So du must be equal to 3/4 dt. So that means 4/3 du is equal to my dt. So I'm actually going to say b is equal to 1500 times 4/3 times, and so now this is e to the u, so this is still e to the u plus c. Put my u back in. 1500 times 4 is 6,000. 6,000 divided by 3 is 2,000. So this gives me 2,000 e, sub my u back in, to the 3t over 4 plus c is equal to my bacteria. So we're now looking at the original function where this rate that they gave us, where this rate came from. So then it's asking us to find the number present at t equals 4. They did give us a little bit of information in there, and I'm going to show you that connection in just a little bit. So when it's present at t equals 4, let's go ahead and plug that in. So this becomes b is equal to 2,000 e to the 3 times my t value 4 over 4 plus c. Oh, we're not going to do that plus c anymore because we're actually plugging in a value. My apologies. So 4 over 4 is going to cancel out, so I'm just left with 2,000 e cubed. Do we have that answer anywhere? Heck yeah, we do. Right here. Okay, so what's the relationship that I showed you earlier? At t equals 0, the number of bacteria present was 2,000. So what does that tell you? When t equals 0, then that means the whole fraction up here becomes 0. So that means e to the 0 is just 1. So I know that whatever this front value is, all this integration to get to this front value had to be 2,000. I could have looked at this question. Yeah, we could have done all this work, but I could have looked at this question if I remember doing problems like this, and I could have said, oh, well, if at 0, it's just going to be 2,000, then that means this has to be that value up front before the e, because e to the 0 is just going to be 1. So then all we have to do is plug in 4, and you get 2,000 e to the 3. So either way, you could have solved it. This way's fine, that way's fine. Let's do one more problem. Okay, so an oil is leaking from a tanker at a rate, here's that word we like, at a rate of whatever RT. So this tells me that really we're saying dr dt is equal to 500 e to the negative 0.2t, 0.2t, but we want to make sure we have it in terms of our dt, so we bring that dt over, then we want to integrate. So this just becomes r is equal to 500 times the integral e to the negative 0.2t dt. Again, you have a little tiny u substitution. So u is equal to negative 0.2t. du is equal to negative 0.2 dt. So negative 1 over 0.2 du is going to be equal to my dt. So this now equals negative 500 over 0.2 times the integral of e to the u is just e to the u plus c. So now I plug it in. But what do I know I'm plugging in? It's asking us the amount of oil that has leaked out after 10 hours. That's a key word right there. After 10 hours means I have to, it's not at 10 hours, after 10 hours. This means I have to evaluate from 0 to 10. So we plug that in. So r of 10 minus r of 0. So negative 500 divided by 0.2, that's the same as saying 500 divided by 5 halves, which is the same as saying 500 times, not 5 halves, 2/5, so times 5 halves comes here. 25 divided by 2. I'm left with what, 1225? Okay, so we have, this becomes a negative 2,500 e, and this was, so negative 2,500 e to the negative 0.2 t plus c. Let's keep that there. Negative 0.2 times 10. We don't need the plus c because we're actually evaluating it. And then minus a negative, so plus 2,500 times e to the negative 0.2 times 0. Well, this is just going to be 0, so this whole thing is just going to be 1. If you plug this into a calculator, because this was a calculator allowed question, this becomes approximately negative 338 plus 2,500, which gives us approximately 2163, I think, but 2160 gallons. We can double check that, see if we got it right. We sure did. Here's our next question, example 5. So here we have an initial value. So if we have an initial value, whatever we solve for still has to be added on, depending on the question, of course, but still has to be added on. So we have a rate given right here, and we know we're looking for how much it will cost 5 years from now. So that is saying at 5 years from now. Okay, so let's go ahead and start. We're going to call our rate, our price, dp dt is equal to 120 plus 180 square root of t. We're going to bring that dt over, and then we're going to integrate. So my p-value is going to be equal to the integral of 120 dt plus the integral plus 180 times the integral of the square root of t dt. So this was just my sum and difference rule, and of course a constant multiple. So this becomes 120t plus 180 t to the 3 halves over 3 halves. Well, if I evaluate 180 over 3 halves, that just gives me 120. So this is actually going to be equal to 120t plus 120t to the 3 halves, of course, plus c. So let's go ahead and figure that out. So what happens at 5 years? So if I plug that in, 120 times 5 plus 120 times 5 to the 3 halves, I get some value. I can't remember 100% off the top of my head. I get 1941.64. Well, if that's all I got, if that's where I stopped, because this is where we've been stopping so far, if that's all I got, well, we got really lucky that the multiple choice doesn't have that as an answer to kind of distract us. But you can tell from the multiple choice that that's obviously not the end. Here's where I said that initial value comes in. Well, if I tack on the initial value, because this is just talking about how the rate of that car has increased in price. So in 5 years, it increased in price by 1,941.64. So if we add the initial value of the car 5 years before, which was 14,500, then we actually get our value of 16,440. And if I double check that, there it is. Awesome. Okay. Moving on, this is from the 1973 BC exam, question 17. So this says the number of bacteria, we're back to bacteria, is growing at a rate. Here's my rate. So dB, with respect to time, tells me right there, units of time, is equal to 3,000 e to the 2t over 5. I bring my dt over. I integrate. So my b is going to be equal to 3,000 times the integral of e to the 2t over 5 dt. Here we have a u substitution. du is going to be equal to 2/5 dt. So 5 halves du is going to equal my dt. So this b is actually going to be equal to 3,000 times 5 over 2 times e to the u plus c, which is equal to what? 6 over 2, 3? Nope, wait, what? 1,500 divided by, so we get 7,500 e, what was my original u? 2t over 5 plus c. Okay, and then it wants us to know that to find the number present at t equals 5. So we just plug in that 5, I plug in the 5, those are going to disappear, and I'm just going to be left with e squared. And so we come here and we look, we have an answer right here, 7,500 times e squared. Again, we had that same information. At t equals 0, the number of bacteria present was 7,500. So if you had seen questions like this, hopefully you developed a pattern and realized that all this work to get this information right here, because it's a pretty easy formula, right? That right there is the basic premise of the formula. So all this work in the front was given to us in the question. Yes, you can solve it like this, but if you remember these style questions, this information is given. So you should be able to answer this question in less than 30 seconds. You say, okay, no matter what, it's going to be 7,500 at 0. It's going to be 7,500 times e to the 0. That's what it's saying. So then if I plug in this value at 5, then that becomes 2 times 5 over 5. Cross it out, so 7,500 e squared. And there we got it. Okay. Okay, this one's a little bit funkier. This one says if dy dx is equal to ky, so that directly proportional constant, directly proportional y, and k is some non-zero constant, then y could be. So this is kind of more of a proof question, and it's asking us to figure out which of these could be my y equal. So that means I have to still do the same thing I've been doing, separate the variables, integrate, solve for y. So let's go ahead and start there. So let's separate that variable. So dy is going to be equal to, this is 1 over y, and then this becomes k dx. We've seen this before. If I integrate those, this becomes the ln of y is equal to kx plus c. I take my e, and this becomes y is equal to e to the kx plus c. Again, I reminded you that this is an exponent property, so if this is plus, that means that at some point we multiply them, so this becomes e to the kx times e to the c. Again, I reminded you before, e to the c is still a constant value. So this is just equal to some constant value, e to the kx is going to be my y. Okay, so this is what we've done so far. But now what we have to do is figure out which of these could possibly be this. So let's start with e. Does this even look close? Well, it has y in it, so if I had to do this, then I'd have to rearrange all of this to include my y. Well, just looking at it, if I rearrange this to have my x separated, I don't think this is going to be this is going to be it. So I can cross that out. Here again, got y over here, so even if I look through my steps, none of this looks familiar. Well, that one looks familiar, but there is a +3, so I'll hold on this one. That one looks kind of familiar, okay? This one would be okay, but the y is on the wrong side again, so we're going to cross that out, okay? So now let's look at our b and our c. Well, we could look at our c and say, okay, so this matches what we have, except we have this +3. And I know what you might think, well, couldn't that just be any constant that we had? You know, don't we always tack on that +3? Couldn't our 3 be it? Yes, I agree with you. However, what did we do with our +c? We brought it in and we brought it to the front. So our +c is already accounted for, so this cannot be it. By process of elimination, it must be b, but how do we know that? Well, what's the only difference? 2 and c. Well, c represents the word constant. So could 2 potentially be this? Absolutely. That's where that comes from. Alrighty. I think one more question I'm going to do. Alright, here we go. A puppy weighs 2 pounds at birth and 3.5 pounds at 2 months later. If the weight of the puppy during the first 6 months is increasing at a rate proportional to its weight, then how much will the puppy weigh when it is 3 months old? So, let's start with what we know. We have a rate proportional. That's pretty easy. So my dw dt is going to be equal to my weight. But we have to have that constant value. We saw this before when I asked you guys to write equations in question 2a. Before it was inversely proportional, but here it's directly proportional. So now we have to figure out how that 2 pounds and 3 pounds relates. Before we do that, let's go ahead and separate these out. Make our lives easier. So this becomes 1 over w dw is equal to k dt. I integrate those. This becomes the ln of w is equal to kt plus c. So w is equal to e to the kt plus c. We also know the same thing we can do here, so we can turn these into 2 multiplications. So this becomes, and again, e to the c would just be a constant, so this becomes c e to the kt is equal to my w. So now I know my original function, but what does that 2 pounds and 3.5 pounds help me? Well, what do I know? At birth, how many months is at birth? 0 months. So I can figure out w of 0, and I can figure out w of 2 months. I don't have to really figure them out because I know what they're equal to. I know it's equal to 2 pounds, and I know it's equal to 3.5 pounds. So what happens if we plug those values in here? If we plug those values in, we can start solving for our c's and our k's. Let's start with our 0. That's always easier. So if my t equals 0, then my w must equal 2. So 2 is equal to some value c, e to the k times 0. Well, that's just going to be 0. This is just going to be 1, so my c value has to equal 2. So I solve for my c. Well, now let's solve for our k. Let's plug in these values. So 3.5 is equal to, I now know my c, so 2 times e to the k times, what was my t? 2. Okay, so now I can just divide that away, bring this over, and then we would just take the ln. So this becomes the ln of 1.75 is equal to 2k, and then I want to divide that out, so k is actually equal to ln of 1.75 over 2. So now I know these two constants, this constant c, this constant k, and if I want to know at 3 months, all I have to do is plug in to my t right here, so let's get another slide. So this is actually saying W is equal to 2e, and my k was what? ln of 1.75 over 2 times t, and we're going to plug in t equals 3. This was a calculator allowed question, so you do that into a calculator. You plug in t equals 3, and you get approximately 4.63. I looked at my answers, and there it is. And let's just see if we were correct, and we were. Okay, the other 3 multiple choice questions in this packet, I believe we can do in class, or we can work through the rest of that free response together. Alrighty, thank you so much for watching 7.9.